In this video, we're going to delve a little bit deeper into the mechanisms of SN1 and SN2 mechanisms, and this is the abbreviation for mechanisms. So we'll remember from Chapter 5 that these two mechanisms are very different. They go by different pathways, they have different transition states, they have different intermediates. What we're going to do in this video is describe the specifics in the SN1 and SN2 mechanisms that we explored in Chapter 5. So let's start with SN2. So as we saw in Chapter 5, the SN2 mechanism is, we call it bimolecular, because there are two species in the rate determining step, the RDS, which means that the bond making and the bond breaking are in the same step. So we have two things happening in the rate determining step. We have bond making, we have a new bond forming, and we have bond breaking. We have a bond breaking in the species. So an example of a typical SN2 mechanism is, say we have NaOH, and we add that to CH3Br, methyl bromide. What would happen, we should recognize now that we have a good OH, which is a good nucleophile. We have Br, which is a halide leaving group. So these two are going to, the OH is going to substitute for the Br. So what we're left with is CH3OH as our substituted alcohol, and we are left with our countersalt of NaBr. So this would be an example of an SN2 type mechanism. We know from Chapter 5 that something like a methyl substituted alkyl halide is going to do an SN2 mechanism because it favors SN2 over SN1. But let's explore the mechanism a little bit further than we did in Chapter 5 and expand it to things that are beyond just Ajax addition to an alcohol. So if we examine the mechanism of this at first, so this is going to, since this is bimolecular, and it's a concerted mechanism, we'll see this happening in one step. So I'll draw my methyl bromide and my OH minus. What we'll see is we have nucleophilic attack on the carbon, and we have the bromide leaving. We saw this mechanism in Chapter 5. So what we'll be left with is a substitution and a loss of the bromide leaving group. If we're to look at the transition state, what we see is we have a CH3, I'll draw this with stereochemistry, that's kind of in the middle. We have an OH on one side, we have a Br on the other side, and what we see is we have two kind of pseudo bonds. So we have the bond making and the bond breaking at the same time. So these both have delta minus charges on them. So we have the bond making, this is the bond making, and we have the bond breaking, both happening at the same time. Again, this is the rate determining step, and we would call this the transition state. Now you'll notice that the OH is attacking from the opposite side, so it's attacking from the opposite side that the Br is leaving from. And we call this type of attack, where one is coming from the opposite side, we call this backside attack. So an SN2 mechanism will always include this backside attack where the nucleophile is attacking from the opposite side that the leaving group is leaving from. What's interesting is we can kind of think of this like an umbrella. So we have the H's kind of over here, and then when the nucleophile comes in and pushes it this way, they're going to flip over to the other side and form a bond on this side. So what we see in backside attack is that the stereochemistry will invert at the point of attack. To draw an example of that, let's do something chiral. So let's say we have a Br, and we'll call this a CH3, and say we have a CH2, so we have an ethyl group, and then we have a hydrogen, and we're adding NaOH to this. So we have our stereochemistry, and we should be able to assign from chapter 4 that this is RRS. In this case, we have one, I'm just assigning a priority of 1, 2, 3, so this would be S stereochemistry. And if we have OH come in, this would be a secondary center, so it's possible that I could do SN2 depending on the solvent. So if we have OH come in, we're going to have backside attack. It's going to attack at this center, push out the BR. You'll see that these groups here will kind of push away from the direction of attack and invert as the reaction proceeds. So you lose Br minus, and what you're left with is CH3 will be down here. Now our ethyl group is on the other side. Our hydrogen is pointing up, or up and back, and our OH is on the attacking side. So you can see it's come from the other side. And if we were to assign stereochemistry to this, we have 1, 2, 3. It goes clockwise, so this would be R. So as you see, we've gone from S to R. We've successfully inverted the stereochemistry, and this is true for all SN2 type mechanisms. If you're attacking at a chiral center, such as we're doing here, then you will invert the stereochemistry. Now, obviously, on the methyl bromide, there is no chiral center, so there is no stereochemistry inversion. But if you're attacking on the chiral center, you will indeed have inversion of stereochemistry. Now, backside attack also has some implications in rate and in sterics. So what we see is that steric bulk impacts reactivity. So we already saw that, say, a methyl halide, we'll just call it general halide, and a primary halide will both do SN2 mechanisms. And one of the reasons for this is because it can't do an SN1 mechanism. That carbocation would be unstable. But also, it is true because if we have a nucleophile attacking, we don't have much on the other side that's blocking this backside attack. We have an R group, we have 3 hydrogens. We don't really have much steric bulk blocking this nucleophile from coming in and doing backside attack. However, if we move to a secondary alkyl halide or a tertiary alkyl halide, we'll see that the rate of SN2 reactions are decreased dramatically, because if we try attacking here, we have bulk on both sides now. We have 2 alkyl groups that's preventing our nucleophile from coming in and attacking. And we see that tertiary alkyl halides really don't exhibit SN2 type mechanisms, because now we have 3 alkyl groups or 3 substituents blocking this attack from happening, this backside attack from happening. So this is why we see, we don't really see secondary or tertiary alkyl halides doing SN2 type mechanisms. We can see SN2 on a secondary alkyl halide if these groups are small, but certainly on a tertiary alkyl halide we will not see SN2 type mechanisms because there's too much steric bulk blocking it from coming in. We also see that even if this steric bulk is nearby, then we will have effects on an SN2 type mechanism. So if we're looking at, for instance, the rate of SN2 attack, say we're doing an OH attack on this ethyl bromide versus this ethyl bromide that has a terbutyl substituent, if we look at this beta position, this OH, we have it's a primary, we only have a methyl group blocking this or potentially blocking this attack. So there isn't much steric bulk blocking this attack, so this SN2 mechanism will be fast. Now this is still a primary alkyl halide, so our primary, our main point of nucleophilic substitution will be SN2, but the rate will be slowed down because we have this terbutyl group, which is very large, near or beta to the position of attack, which is additionally going to cause steric hindrance and block this from happening. So we would say that the rate of this one, of the non-substituted alkyl halide, is going to be much, much faster than the rate of the terbutyl substituted alkyl halide, because we do have steric bulk near the point of attack, or sometimes called branching near the point of the attack. So that's what an SN2 type mechanism looks like. Let's examine further the SN1 type mechanism and implications of an SN1 type mechanism. So this is going to be SN1. As we saw in Chapter 5, SN1 type mechanisms are unimolecular in their rate law. That means the RDS has one molecule. Remember, the rate determining step is going to be the breaking of that carbon halide bond to form the carbocation. And what we see is this is not concerted. So this is going to happen in multiple steps. So let's look at the overall mechanism. So say we have a classic example, excuse me, of a SN1 type mechanism, and say we have H2O. We would do the substitution, and we end up with the terp-butyl alcohol and HBr as our resulting counterproduct. To examine the mechanism, we see that in an SN1 mechanism, we see the first step is going to be the leaving group leaving. That results in loss of Br minus, and we are left with the tertiary, in this case, carbocation. Remember, this is going to be the rate determining step, the loss of a leaving group to form the carbocation. So depending on how stable this carbocation, we will determine the kinetics and the activation energy of this step here, how fast this is going to be. In this case, we have water as our nucleophile. So we're going to have attack of the nucleophile on the carbocation. There is an extra step in this because we do have, since we do have water as a nucleophile, we will end up with a protonated oxonium ion as an intermediate. And that can simply be remedied by deprotonation by base. In this case, there's bromide floating around, so it'll probably be deprotonation by bromide. We will push those electrons back onto the O, and we've completed the cycle. We lose HBr, that's right here, and we generate our alcohol. So again, rate determining step is the formation of this carbocation. So this is why this is only with secondary and tertiary alkyl halides, because the primary and the methyl carbocations would be unstable. And that would be the rate determining step for this. So this is really what's determining the kinetics of this reaction. Now, one of the defining characteristics of the carbocation is that if we look at this carbocation here, and I'll draw this with stereochemistry. Let me erase this. I'll draw this carbocation with stereochemistry. What we see is that this carbocation is going to be sp2 hybridized, so that means it's planar. So this is our terp-butyl carbocation that I've drawn with stereochemistry. So we have an empty p orbital that holds a positive charge, and we have our three methyl groups. I'll just draw those in that are planar. The implications of this mean that the nucleophile, say we're doing the same example, we're doing water. Unlike in an SN2 mechanism where the stereochemistry is specified in this step, we have to do backside attack, we see that there's no preference for which lobe this water attacks. It could come from the top, or it could come from the bottom. So as a result, stereochemistry is not maintained if we have a stereocenter. It turns out that in this step, stereochemistry is going to be scrambled. So looking at an example of that, say we have this secondary alkyl bromide, and we add H2O. What we'll see is we get some amount of backside attack where the stereochemistry has been inverted on that position, but we will also get some amount of stereochemistry retention. This type of mixture, this is a racemic mixture, meaning the enantiomers are mixed together. We see that these are two enantiomers. We see that these are inverted, and one way of writing if we want to write the fact that there's a racemic mixture of two enantiomers, we can draw that stereocenter with a squiggly line. So that indicates that you have a racemic mixture rather than writing out both enantiomers. So this means we have both towards us and away from us in the mixture. So because we have this empty p orbital where the water or the nucleophile can attack from both the top and the bottom, we do see scrambling of stereochemistry in an SN1 type mechanism. Unfortunately, there are some complications that come up with an SN1 type mechanism that do not show up in an SN2 type mechanism. So let's look at another example. Let's look at this secondary alkyl bromide, and we add water. This looks like a normal SN1 type mechanism, so we would expect to see scrambling of stereochemistry right at this secondary position, and we would expect to see HBr. However, this is not the major product out of the reaction, and to show you why, we're going to have to look at the mechanism. So in an SN1 mechanism, the first step that happens is the leaving group will leave, so we'll break this bond and form the bromide and the carbocation. So this loses bromide, and then we're left with the carbocation. So what happens, if we look at this structure, we see that there is a hydrogen right here, alpha to the, or beta to the position that has a carbocation. What happens next is called a carbocation rearrangement. So the principle behind a carbocation rearrangement is we want to have the most stable carbocation that can form in a possible circumstance. So we look at this and we see that this is a secondary carbocation, which is stable. We learned in chapter 5 that a secondary carbocation is stable. However, if I move this hydrogen one carbon over, making the carbocation shift, we'll then have put the hydrogen here, and we'll move the carbocation here. We've now gone from a secondary carbocation to a tertiary carbocation. In terms of stability, the tertiary carbocation is much, much more stable than the secondary carbocation. This type of rearrangement is called a hydride shift because we're moving a hydrogen from one place to another. And this will occur if and only if we can stabilize the intermediate. We don't see hydride shifts if it doesn't do a productive carbocation rearrangement, but if we can go, say, from a secondary to a tertiary carbocation, a hydride shift will occur. So as you can imagine, we do the OH addition, or the water addition, and what we see is our major product is this tertiary alcohol, not this secondary alcohol. So this would be an example of a hydride shift. If we look at other groups can shift as well. If we look, for instance, at this alkyl halide, and then we want to add water. Again, the first step is the same. We're going to lose bromide. And then we will be left with the secondary carbocation. In this case, we have a CH3 group beta to the position that can move. If we looked at the other side, we do have 3 hydrogens here, but if we were to do a hydride shift from one of these terminal positions, we would end up with a primary carbocation, which is less favorable than what we started with. However, if we move this methyl group over 1 carbon, we'll see that we've now moved this methyl group and we've shifted the carbocation. We've gone from a secondary to a tertiary carbocation. Again, this type of move is called a methyl shift because we moved a methyl. And what we see is we don't have the alcohol substitution at the original position, but we do see alcohol substitution forming this type of alcohol, with the the tertiary alcohol forming. And this is because we had a carbocation rearrangement that stabilized the carbocation intermediate. So the main point here is carbocation rearrangements only occur if it can stabilize the transition state or the intermediate. So again, if it would go from a secondary to a methyl or a secondary to a primary carbocation, it won't happen. However, if we can somehow go from a secondary to a tertiary carbocation, increasing the stability of that intermediate, then we will see a hydride or a methyl shift We can see higher order shifts. They're just generally slower. But these are fast because they're intermolecular, and since it's favorable to stabilize the carbocation, these, if they can occur, they will occur. So this is one thing to be aware of in SN1 mechanisms, and we'll see other mechanisms that this comes up with in future chapters. Whenever we form a carbocation intermediate, we run the risk of having rearrangements in the molecule. So this is just something to be aware of when we're looking at SN1 type mechanisms.